This PowerPoint is over momentum and collisions. So the topics we're going to discuss are going to include momentum and impulse, conservation of momentum, and then specific types of collisions that conserve momentum. All right, so momentum and impulse. So let's talk a little bit about what momentum and impulse are. First off, when a net force is being applied to something, it causes it to accelerate, so it gets faster and faster. Momentum kind of describes its motion, while impulse kind of describes the force that's being applied. So it's applied over a certain amount of time, so that force times time delivers an impulse. Now to kind of look at the equation, we have final velocity equals initial velocity plus acceleration times time. We know that equation from kinematics. And then the acceleration is going to be equal to the force divided by the mass. That gets plugged in there. And we get this equation right here. Now we rearrange, and you can see that with the initial velocity to the other side, and then we multiply by mass. So final velocity minus the initial velocity, and then when we multiply both of those by mass, we have this right here. Now the net force times time, that is going to be the impulse. The mass times final velocity minus mass times initial velocity, that's going to be our change in momentum. Mass times velocity is momentum. All right, so net force times time, that's our impulse. And then mass times velocity is momentum. So mass times final velocity is final momentum. Mass times initial velocity is initial momentum. So final momentum minus the initial momentum, that gives us our change in momentum. Okay, so change in momentum is going to go there, and then net force is going to be equal to, or net force times time is going to be equal to change in momentum. Again, net force times time, that's impulse. Impulse equals change in momentum. All right, so momentum being a vector, that means the direction has to be taken into account, which means an object moving to the right at 3 meters per second, if it's moving to the left at 3 meters per second, it has a different momentum because it has a change in direction. So if you have a final minus initial, you have to include that direction in there with the change in momentum. All right, so a little bit more, Newton's second law. Let's kind of see where Newton's second law takes us in order to find for the relationship between impulse and momentum. All right, so net force equals mass times acceleration. We go ahead and plug in. You can see right here that if we take the mass and acceleration, mass and velocity, the change of velocity times mass, that gives me change of momentum in the numerator, and then we take that time over to the other side, we get net force times time. That gives us our impulse. Now, what's interesting about this is actually Newton's second law. Newton's second law, we say, is net force equals mass times acceleration, this one up here. But actually, Newton said this. He said that it's the rate of change momentum. The net force is equal to the rate of change momentum. Not in those words, but effectively he said the net force is the rate and change of momentum. But you can see how we get from net force equals mass times acceleration over to change in momentum over time. And a lot of times we talk about acceleration is a little bit easier to discuss, so we use this equation a lot of times when we're talking about net force equals mass times acceleration. But realize that Newton actually said net force is the rate of change in momentum. And if you think of a calculus term, it's the change in momentum divided by time, so dt and dp dt. All right, so a 12 kilogram hammer strikes a nail with a velocity of 8.5 meters per second. It comes to rest at the time of 8.0 milliseconds. So what's the impulse? What's the impulse given to the nail? Give you a second to do that. All right, so two different ways of finding impulse. Impulse is net force times time, but impulse is also change momentum. So if we get the velocity and the mass, then we can do a change of momentum. So impulse is going to be equal to that change of momentum. The change of momentum of the hammer is misspelled, sorry about that. So change of momentum of the hammer is the opposite of the change of momentum of the nail. So if we take the mass, multiply by the final velocity minus mass times initial velocity. So the final velocity is 0, and then the initial velocity of that hammer is 8.5, so we multiply that by 12. And then we get the impulse is going to be equal to 102 kilograms meters per second. And that's going to be the units for change of momentum and for momentum itself. Impulse, you can see, is going to be net force times time, so it's going to be Newton seconds. So kilograms meters per second and Newton seconds actually gives you the same units. All right, so what's the average force on the nail? The average force, if you take that the equation we had on the previous slide where net force equals the rate of change of momentum, then that means you take the change of momentum divided by time. That's going to be 102 divided by 0.008 because it's in milliseconds. It's got to be converted to seconds. And then we get a net force is going to be 12,750 newtons. All right, so this question, the area under a curve for a force versus time graph represents what? Okay, so a couple different answers here that you think it could be. First of all, work is force and distance. Energy is related to work. So force and displacement is work. That's not force and time. So force and time relates to impulse, and it kind of relates to momentum. However, it's not going to be momentum because impulse equals a change in momentum. So the change in momentum will be equal to impulse. So impulse is actually the area of a force versus time graph. All right, so why do we use impulse as opposed to just using kinematics where we have force, acceleration, final velocity, initial velocity, and all those? Because sometimes we don't have a constant force. Newton's second law works really well if we have a constant force and we have a mass and we have an acceleration. But if we don't have a constant force, then impulse helps us out. What we can do is we can measure the force over time, and that force over time, if we take the area under that, will give us impulse. So if we have, this much force for a short period of time, and then we drop down and have this much force for a short period of time, we can take the area of each one of those, add those impulses together, and that will be equal to change of momentum. So we don't have to figure out the average force, we just have to figure out the total impulse. All right, so collisions between moving objects. So let's say we have this object right here, this large M and this small m. The large M has a velocity 1, and the small m has a u1. So that's another velocity, just using a different letter for it. All right, and then afterwards they stick together. So the velocity of both of them are going to be the same. All right, and then in between they stick together, and then afterwards the spring pushes them apart. So they have initial velocities and final velocities for each one. Okay, so while they're in contact with each other, notice that Newton's third law is taking into effect, which means that large M is applying a force on small m, and small m is applying a force on large m, and they're both going to be equal and opposite. Not only are they going to be applying the same force but in opposite directions, but they're also, large M is in contact with small m for the same amount of time that small m is in contact with the large m. So if we take the impulse, all right, and we multiply each of these forces times the amount of time that they're in contact with each other, then you see that the impulse of small m and the impulse of large m are going to be equal and opposite as well. So if I take one of this negative to the other side and I literally add the two impulses together, it should be equal to 0. Not only that, but that means if I take the change of momentum, since impulse equals change of momentum, then if I take the change of momentum of each object and add them together, I should get a total change momentum of 0. All right, so that means that the change of momentum of the small mass, is going to be m u2, the final, minus u1, the initial. And then that's going to be equal to negative large mass, v2, which is final, minus v1, which is initial. Okay, and then looks like they distribute here, and then a little bit of rearranging, and you can see that the large mass times v1, which is the initial velocity, and then small mass times u1, which is the initial velocity. That's going to be all the initial momenta actually. So, and then mass 2, the large mass times velocity 2, plus the small mass times u2, that's all the final momenta. So all of the initial equals all of the final, which effectively gives us conservation of momentum. So momentum is going to be conserved. Now there's a little bit of caveat to this. There's something you have to remember, or at least recognize. In order for there to be a conservation of momentum, there has to be no outside forces. Effectively, these forces need to be the only forces that are acting on these two objects. As long as those are the only two forces acting on the two objects, then their changes of momentum will be the same. All right, well, one will be positive, the other will be negative, but they'll have the same magnitude. But if there is an outside force on one or the other, then momentum is not going to be conserved. Give you an example of where momentum will not be conserved. If I have, let's say I have this mass right here, I put a wall right next to it, or maybe this mass I'm actually physically holding on to. Then when this mass comes and hits it, then that mass is not going to have a conservation of momentum because it wasn't allowed for this mass to have the forces to be equal and opposite, and there's different masses applied to the small mass than the large one. All right, so again, momentum's conserved. as long as there's no outside net force. And there's two ways of thinking about conservation momentum. Either you take the two changes in momentum and add them together, that'll be equal to 0, or you take both of the initial momenta and then that'll be equal to both of the final momenta. Generally speaking, I probably use this bottom equation most when I'm looking at the before and after. It makes it a little bit easier because I don't have to deal with the parentheses and whatnot. Also, everything is positive, and the only time I have to make something negative is when the direction is in the opposite direction. So these, you can see in this example, they're all positive directions, so I would just make everything positive, and then it'll work out with my math. All right, so let's say we have a collision with a stationary object. The two objects stick together. What's the final velocity going to be? All right, so let's say I know the initial velocity. I know the mass of each one. So what's that final velocity? What's going to be the equation for that final velocity? All right, so before and after. I take all the momentum initially is from mass, the large mass times velocity. The small mass had no velocity. And then afterwards is both masses together times their velocity. Now, you could treat each object separate if you'd like. But when they're stuck together, you can actually treat it as one object for after. All right, so it's mass 1 plus mass 2 times velocity. Now, if you treat them as separate objects, it would just be capital M times V plus lowercase m times V. And if you factor out the V, you see you pretty much get the same thing. I like to think of it as both of them are now one object and we treat them as one object. So that's our equation. To solve for the velocity, you get this equation. All right. Now recognize that this equation basically tells us that the numerator is the total momentum initially, and then we divide by the total mass, and that gives us the velocity. All right, so we got a 9,300 kilogram boxcar traveling at 15 meters per second, strikes a second boxcar at rest, and the two stick together and move off at a speed of 6 meters per second. What's the mass of the second boxcar? All right, I'll give you a second to try this. All right, so we have an initial velocity of the first car. The second car is at rest. So we know we can figure out the initial momentum of both objects. And then when they stick together, we know the final velocity, right? Now the second boxcar, we don't know the mass, so we got to keep that as our variable. And that's going to be a variable on both sides. So the initial momentum and the final momentum, right? All the initial momentum is in the first car. So it's going to be that 9,300 times 15. And then afterwards, when they stick together, the two masses are going to be together, but we know one mass, but we don't know the other. So since we know the velocity, we can divide by that velocity, and then that isolating for your mass, they like to isolate for the variable first before they plug in numbers. I would actually go ahead and put the 9,300 times 15, divide it by 6, and then subtract off that 9,300 again, and that'll give us our mass of the second car, which is 13,950 kilograms. All right, so now a bullet is fired into a block that's at rest. So what is going to happen with the bullet and the block? All right, so something you need to recognize is the bullet, when it hits the block, is not going to be at rest. That's one of the misconceptions with this, is they think I get people who say, well, the bullet stops. Well, it doesn't necessarily stop. It actually embeds into the object and moves with it. So it still has a final velocity. So the two objects effectively stick together. So before and after, our initial momentum before is all in the bullet, and then the final momentum is both of the objects together times the velocity. All right, so then we solve for the velocity, we get the same equation we got before when two objects stick together. So whether the bullet embeds itself or the two objects stick and move off together, either way, it's the same equation. Freight car moves along a frictionless level railroad track at a constant speed. The car opens the top. The large load of coal is suddenly dumped into the car. What happens to the velocity of the car? I'll give you a second to do this. All right, so what's going to happen? Well, something you need to recognize is momentum is a vector, which means whatever happens vertically is independent of what happens horizontally. So we're assuming with a frictionless surface that when something is dropped in there, the vertical doesn't really change anything. All right. Now there's no conservation of momentum vertically because the ground pushes up on the car, preventing the car from moving downward. So the coal that comes down initially has momentum, and because the ground is there and it hits it, then everything stops. So it loses momentum, and momentum is not going to be conserved because you had momentum before vertically, and then you have zero momentum after. All right, that's an example of an outside force that's that interferes and does not conserve momentum. But horizontally, we have no friction, so horizontally we're going to conserve momentum. So what's going to happen? Well, if you think about it, the coal has no horizontal velocity, but the car does. So what happens? Effectively, what happens is it's the same as one object that's moving, hitting the other object, and then the two moving together, except one is dropped in there. So then the mass of the car effectively increases. So if momentum is conserved and the mass of the car increases, then the speed has to decrease. So it's going to be C.